Good afternoon, everyone. This is Tuncer Baykaş, IEEE Turkey Vice Chair. Welcome to the second session of TUAC, our undergraduate academic conference. And we have a distinguished speaker today with us, Professor Peter Fuhr from the Oakland Ridge National Laboratory and University of Tennessee. So Dr. Peter Fuhr has been involved in industrial wireless sensors, secure systems for 30 plus years as a NASA space optical physicist, as a university professor, serial entrepreneur, and researcher. In his role as subject matter expert for smart grid secure communications, he has written and delivered numerous briefs pertaining to the electric utilities implementation of advanced technologies that have been presented to the Department of Energy, FCC, and Congress. So you may feel that his projects included embedding sensors to airplanes, such as Boeing 787, or dams, such as Winooski 1 dam, or the famous F-22 Raptor, but also hot air balloons, spacecrafts, nuclear power plant containment vessels, even humans. So his recent activities have included R&D pertaining to sensors and systems appropriate for environmental monitoring of fracking, water quality sensing for industrial enterprises, sensing and communication systems for operation in harsh environments, and examining intricacies of printed electronics in additive manufacturing environment. He's a distinguished scientist at Oak Ridge National Laboratory, a grid communications and security group leader, and also serves as the technology director of the ORNL, Unmanned Aerial Systems Research Laboratory. He's a fellow of International Society of Automation, and finally, he's a professor of electrical engineering and computer science at the University of Tennessee, serving as graduate student doctoral advisor. Professor Fuhr, thank you very much again for accepting our invitation. And we donated one sapling for you. So you have a tree in Turkey. I hope that you can actually visit it sometime.
That is so kind of you.
Thank you very much.
Thank you.
So, yeah. And the floor is yours, sir. Thank you.
Oh, yeah. Thanks a lot. Okay. Hi. So, let's see if I can, let's try to share a screen. Let's see if I could figure this one out. Let's go this. Maybe it's 2 clicks. Okay, success. Can you see a PowerPoint slide?
Yes, we can.
Here you go. Let's just start right here. So the map is showing where we are in the respective parts of our obloid spheroid, the Earth itself. You're there, I'm here. And through the magic of electrons and photons and all sorts of other stuff, here we go. So thank you for the quick introduction. I'm the old guy here. So I've been around doing stuff for quite a while. And let me just hit a couple things. One of them was, I have an undergraduate degree in physics. That sets the stage. And then I also have an undergraduate degree in mathematics. And then I have master's and PhD in electrical engineering from a specific university in the northeast side of the United States called Johns Hopkins University. And while I was going to graduate school, I was also working. I was working at NASA, the space agency. And so in those particular things, my dissertation topic involved, that's a long time ago, it involved optical communications between satellites. And we designed lasers and put them up in space. And if the conditions are right, I can see 2 satellites I worked with flying overhead, and that's kind of fun. And since then, there's a lot of other stuff. I have a lot of slides here just to cover, because I'm trying to represent what's happening at this national lab. So let me set the stage just a bit. I have videos, we'll see if they play or not. Some of the stuff we're going to talk about are drones, okay? But get back there, get back there. This is the first known drone in 1917. And they've sort of progressed since then and sort of not in some respects. Anyway, there's going to be some themes here, because what I'm trying to do is represent some of the activities that our 5,500 colleagues here at the National Lab are doing. So with respect to what is this Oak Ridge National Lab, what is this place? What do they do? Excuse me. So here in the US, we have the Department of Energy, and the Department of Energy, big surprise, is major focus is keep the lights on. How do we do that? And optimize the grid and generation and distribution, all the things associated with power. But that's a small fraction of what the lab actually does. The Department of Energy in Washington, D.C. operates 17 national labs across the United States. And in size-wise, the United States is about the size of all of Europe. So you get some feeling that, yeah, stuff is spread out here and there. We are the largest office of science laboratory in the United States. And as I mentioned, we have 5,500 colleagues. And I am extra fortunate that Professor Ali Reza Ekti has joined us here at the National Lab to help us solve some various problems. And we'll get to that in a bit. So I'm going to represent some of the activities that many people that we work with are working on, some in more detail, some in less. As I mentioned, I have an awful lot of slides, and we'll make them available to you so you can do whatever you'd wish. Let's get going. Some of the activities that we have underway is we're working with pulsars. And in a pulsar situation, what we're thinking is the following. GPS, or in general, those global navigation satellite systems, are susceptible to all sorts of issues. We already know that. You know it. We know it. You know, I've been hearing how on the north coast, well, I guess you'd say, well, anyway, the southern end of the Black Sea, the north coast of Turkey, GPS gets jammed a lot. And we get all sorts of issues here in the US. Big surprise. So we've been investigating the idea of using a millisecond rotation pulsar because it's hard to jam a rotating neutron star. And that activity is underway. And we've been able to actually get very high timing. In fact, better than atomic clocks, better than cesium, rubidium, the other stuff, using pulsars. And we're trying to get that into a small satellite dish that could go inside an electrical substation and either serve as the primary or backup timing source to keep the grid lights on. That's a pulsar activity. That's it for now. If you want more details, you can contact either Reza, apologies, Ali, if I'm mispronouncing it, or myself. We give you more details. In cybersecurity land, we have quite the effort. And we're doing some things that are a little different. One activity is called synesthesia. And we'll get to that in a minute. The other thing is steganography, and those two, we're working them together. And steganography is well known as a way to put information and hide it inside a picture. And we're working on that. We got sensors. We have all sorts of additive manufacturing. SCADA systems, you can read this slide as well as I can. But the bottom line is that we have over 5,000 employees in this fairly large facility, 35 square kilometers, where we're doing all sorts of stuff. Let's try to see a movie. So here's the lab. Let's see what we can do. Let's see if the video plays. Sometimes it does. Sometimes it decides not to. Oh, it looks like it doesn't want to play right now. That's okay. What we're going to be covering in this stuff is this. And hey, and all you double E's, congratulations, you chose the right discipline. You really did. I noticed you were thinking, maybe I should be a physician. No, forget that. It's electrical engineering all the way. Physics has the underpinning, sometimes throw in a little bit of chemistry, et cetera, et cetera. And so we refer to this particular slide as a doctorate, a PhD in a single slide, because if you can master this stuff, hey, you're doing great. So what do we have? Well, a lot of it is communications related. As you can see in the lower right, there's amplitude shift keying and frequency shift keying and mesh networking and antennas. And I thought it was just, very nice. There's all sorts of stuff that goes into trying to put together a system that's going to solve some particular problem. And that's what we're after. I think it's today, maybe it's earlier today. Let's check the schedule. There. It looks like right out of the gate earlier, there was a presentation involving rotating Vivaldis. Those are great antennas. So it's good to see that. Antenna theory comes into play quite a bit. You can see other things that are happening here between direct sequence spread spectrum. And of course, here comes the other stuff that you can get all sorts of different spread spectrum activities and multiple access stuff. Bottom line, again, all of this comes into play. But what I want to highlight again and again is at the very top of this screen, right there at 12 o'clock, it gives you a simple equation. And you have amplitudes, you got frequencies and phases, and it always comes back to that. So that's what we need to cover. And that's what our colleagues cover, sometimes not all the place. What the heck is this? Well, some of our colleagues have been doing additive manufacturing, and we 3D printed this Cobra, this car. Now, it's got electric drives in the wheels. So that's it. My team and I were lucky enough, let's say that, to actually build the electrical wiring harness for this car. So the wiring is not printed. The motors weren't printed, but the structure, the fuselage, the frame itself was 3D printed. And you can see a picture on the lower left-hand or lower right-hand side when we had President Obama and Vice President at that time, Joe Biden, down here at the lab. And, they wanted to drive the car. It's like, you can't drive this thing. Other things, it's really shiny, isn't it? Well, if any of you have 3D printers, sometimes you get sort of like a corrugated structure. So it's not smooth. Well, that was the case. So we printed this car, but it wasn't as smooth and shiny, certainly not shiny like it is right now. So what did we do? We hired 2 undergrads to polish it. And they had sandpaper of varying degrees of fineness and got this super smooth finish. And then we printed the darn thing. I give credit to a colleague of ours. His name is Lonnie Love. And what Lonnie did was prove that we could print this in the laboratory setting. But then he took the printers, huge, it's an out of the box, big printing machine, took it to a large convention center in Chicago, it's center part of the US. And it's well known that there's it's not automation. What is it? Manufacturing conference that takes place. And in 8 hours, they printed a car on stage and drove it off. And it's proving the concept that, we can have 3D printed vehicles. We did that. But why stop there? So the next deal was, hey, let's print a house. So on the left-hand side, that's actually a house. And we printed all the furniture and everything in there. The appliances we just got off the shelf. That house, underneath the steps going up, is a really large battery. On the top, you can just start to see it on the top of this thing are solar panels. And the car on the right-hand side sort of looks like a Jeep or some sort of, that vehicle. We've 3D printed that vehicle also. And the main thing is you can run the house off the car, off the vehicle. You can run the vehicle off the car. And again, it's proving a concept that, we could 3D print houses that already have renewables inside them. All sorts of stuff. That's what you can do when you have a reasonable budget and you have 5,000 people working on this stuff. Well, about 2 weeks ago at the lab, Oak Ridge National Lab, we finally put in place this particular computer. It's called Frontier, and then ran it and used some specific performance testing, and it's the fastest machine on the planet. It's really something. What it can actually do, that's a deal. It is, I don't know what the conversion is, so apologies. This computer cost $375 million, and it is 1 acre in size. You go to Google, you can do the conversion. Bottom line, this thing is a big computer, and it can do a lot of stuff. It's pretty fun. We have other things that are underway. So at the National Lab, again, the major focus is keep the lights on. So you can see in the pictures here, all these different types of technologies and applications that come into play. And Ollie and I and our team, we've been involved with this, for quite a while, and away it goes. The graphic in the middle is just, a pretty picture. This is stuff around the outside. That's where the R&D is taking place. Now notice this. It's going to disappear in a minute. I think it's on a timer. Yeah, here we go. So we got asked a few years ago about, as it says in the upper left-hand side, precision agriculture. And the idea was, can we reduce the amount of pesticides and or chemicals that are put on crops in the field via using drones? And have the drone just know what it's doing. And indeed, we've been working on that, and it works incredibly well. The bottom picture on the left-hand side, the opposite side of the US, is San Diego. Lovely climate right on the Pacific Ocean. And San Diego Gas and Electric, as you can see in the chart and the text there, we're talking about that picture in the lower left-hand side. We're using drones for looking at electric lines and gas lines and doing all sorts of stuff. The other two, mine, and we got it, you got it. A major deal about the lab is our fundamental mission, and the other national labs too. We do not compete with the private sector. We can design stuff and we can get it towards a product, but we can't sell it. That's not what the lab is doing. We try to tackle international important questions, big questions, and then use these facilities and resources. And we have hundreds of individuals from around the world that come and work at our place. Oh, all sorts of stuff. It's pretty good. There are a couple other things. We've been looking at drones for, as you see, the right-hand side, vegetation, etc. But let's get back to what the lab is really about, and let's keep the lights on. So we've been flying drones for years and measuring various parameters, electrical field parameters. For example, on that drone in the upper left-hand side, we mounted all sorts of cameras, thermal, IR. We're trying to do a UV camera. We had electromagnetic sensors measuring electric fields, magnetic fields, ambient conditions, all this stuff, and bring it into close proximity of the transmission and distribution stuff like transformers. And can we monitor their health and performance via a drone? And of course we can. But the main thing is we don't treat it like a camera. We treat it like a platform delivering some sensors. So here's something we did 5 years ago. And oops, let's go back, come on. We have drones on top of drones. And just looking down, now this is, get back here. Now this is at an electric utility, and we're flying in close proximity to these lines and seeing stuff. We have many choices, as do you, for types of drones. And we were helping organizations just try to figure out which ones are best for mining, both open pit mining or go into tunnels. And yeah, we've flown all sorts of drones and that stuff. Here's some of the junk. We were using inexpensive thermal sensors and looking down from the sky. That's that blurry picture at about 7 o'clock on this diagram. But underneath it shows lots of stuff that we're actually measuring, lots and lots of stuff, lots of things to do. Again, here's another video. Come on, where's the pointer? Hello. Let's see if it plays. Doesn't look like it wants to. Maybe it will. We 3D printed that carriage. It's carrying all sorts of sensors. Notice the date, September 7th, 2017. We're flying drones at the training site. We're looking at their stuff from the SCADA system itself, right, the distribution center. If you recognize it, that is a Chinese-made DJI Phantom 2. Lots of sensors inside that little package on 900 megahertz communication stuff. We used a super inexpensive thermal imager that's blurry. That's the thing on the left, because you know what we can do, and you can do it too? Use mathematics to clean up the image, and away we go. Meanwhile, 8 kilometers away, this is what they were seeing live in the SCADA system. We were just there 2 days ago again, and they want to remote control the drones from the distribution center itself. We'll be working on that starting in 2 weeks. Won't we, Ollie? Yes, we will. There's a lot that goes into this. It may not seem like much. There's a lot. We have a great partner in this utility. For you communication buffs, here's how it worked: optical fibers, communications, SCADA systems, video, all sorts of stuff that goes into this. And again, if you need more details, well, we have some presentations and stuff. This is the utility that serves about 215,000 customers. We work with them all the time. So what's been of interest lately is looking at swarms for wildfires. And really, maybe some of you are involved with this also. Yeah, this is going to take a moment. This is just generic. Think of the stuff in the box. There's your drone. There's your unmanned or unpersoned aerial vehicle. It's got a flight controller. You can see it's got GPS nowhere. There's a little camera, some sensors. You can use your little handheld unit and talk to this thing and control it through the transmitter at 2.4 gigahertz. Why? License free worldwide, baby. No license. You can have a ground control system, and authorized frequencies in the United States are at 900 megahertz. So that's how we talk to a single drone. Here's how you can do it to multiple drones. So simple. Frequency division, multiple access. You use 900 megahertz for the one on the left. You use 902 as the carrier to go straight up to that drone number 2, and use 904 megahertz to communicate with the drone on the right. It's all simple. In a mesh configuration, in a swarm configuration, what's really happening here, people are just reusing what's going on with wireless sensor systems, wireless mesh variants. I mean, all sorts of stuff. We all work in wireless, we all work in sensors. Here's how we get them to talk to each other, different topologies, same thing up in the air. Just treat the drone like another IoT device. Pretty easy. And that's it. So what do we have going on here? Well, you could talk to the drones via cellular. And this is how it works. All of you know that. Certainly the professors do. This is how you communicate that way. And we've actually put it together. And we're using a specific protocol. You can see at the bottom, open source, baby, open source. And it's called MAVLink for micro air vehicles. And we have it running on the flight controllers. Those are the flight controller guts that are out of a couple different types of drones, specifically from 3DR. They're good. And bottom line is you can get the drones to talk to each other, and you only then have to talk to one of them, and it'll pass on the message. Where's this coming from? It's coming from wireless sensor networking topologies. It's hard to see it. Maybe you can see it better than I. On the upper right-hand side, around 1 o'clock on this diagram, you see 2 drones that are flying. If you look down on the table, there are a few more that are there. So a few months ago, we were in Northwest United States in Montana, where it's beautiful. And we were there in the fall, and we were flying some drones in a swarm configuration. These things were too light. So the atmospherics weren't bad. Slight winds, not a big wind. They had trouble, but it's proving the concept the way we could go. Yeah, you're doing lots of stuff. Yeah, big deal. Plume modeling, that picture on the right-hand side, we have activities looking at bad chemicals and other stuff that may be in the atmosphere due to who knows what. So remember that big computer, the thing that costs like $375 million? We use that. And by we, it's not Ali or myself or a team. It's other people we talk to. And they use it for plume modeling to see where the smoke or the chemicals are going, et cetera. And there's a represented model in the upper right. Again, hey, I think some of you are undergrads. Comes back to this. There's your dissertation. Everything is inside there, sensors and systems. And remember, there's really just one equation. Now, you physicists, you're going to get over here and start banging on me and say, no, it's perturbation equations and fill in the blank, Hamiltonians. Simplify it. It's this. You got an amplitude, a frequency, a phase, and we can mess around with it. We can have a parameter of interest, modulate one of those things. You have an amplitude or intensity-based sensor, or you can do communications. It's that equation. It's that one. We did a bunch of stuff with spectrum analysis. Big surprise. Get a spectrum analyzer, go out and see what's happening. And this is just looking at the ambient condition where we've been flying drones. There's a lot of stuff going on here. We're 2.4 to 2.5 gigahertz, basically. So you have Wi-Fi and Bluetooth and sensors and systems and all sorts of stuff. And graphically, it's kind of interesting. We have other activities at the lab. And we have a certain guy named John Greenhill. He's in Washington, D.C., and he's helping us direct what we're doing with respect to coronal mass ejection. So hold on a second. We just went from this slide, has wireless and sensors and communications and blah, 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 to this thing, to this. Again, the lab is big. There's lots of activities that we're looking about. And this, coronal mass ejections, and what happens on the Earth, notice it's over here where the pointer is on the right-hand side. That's a geomagnetic disturbance. And you can actually change the voltage of the Earth itself if there's enough energy coming out of the sun with coronal mass ejection. The distortion is happening there. You can see that's the magnetosphere that's protecting us. Thank you very much, magnetosphere. Keep the solar flares away because they can cause all sorts of havoc. There's some great YouTube things and other, gloom and doom for the planet if we don't do this right. So there are 2 satellites that are halfway between the Earth and the sun, and they're looking at these things all the time. They're looking at solar flares to look to see if there is indeed a coronal mass ejection, a bunch of charged particles coming out of the sun, aimed right at you. Well, me too, aimed at the planet. And it's interesting. We did some work here at the lab to support specific types of sensors to measure these energetic particles. Again, it's a big place, lots of disciplines. There's a video that shows that video we looked a little while ago and other stuff. We wrote a paper about it. Yeah, let's publish something too. Away we went. We did some stuff with fracking because the question was, okay, that's great. Let's pop some holes in the ground. And when we do that, we can get some all sorts of stuff. We get methane that comes out. We got carbon dioxide that's released, hydrogen. You can see this inside here. We're really after those hydrocarbons, and away we go. There are lots of wells. In the picture on the lower right-hand side, I was in an airplane in West Texas a couple of years ago, and just looking down, every one of those little dots, that's not a house, that's a fracking site. And as you can see, the data shows that as of 3 years ago, there were 63,000 plus fracking pads in the US. And our concern is, okay, great, get the chemicals out, the hydrocarbons, maybe it'll drive the price of gas down. It's crazy here. I mean, it's even crazier where you guys are. So we could do that, but you don't get something for nothing. There's a bunch of nasty chemicals that come up, and we have some drones that can fly around and measure stuff because the companies don't like us out there saying, hey, you have a leak over here. You should go take care of it. But regardless, we're doing it. We're measuring lots of stuff with our particular UASs. We have some that go in the water, some that work like little submarines, certainly ground rovers, but let's get back in the air with all sorts of stuff. And these are some of the stuff we're measuring. Radiation, we got magnetometers, all sorts of stuff to measure parameters of interest. Where'd this come from? What the heck is this? Okay, look, there's currency. We don't call them bills. They're the banknotes. And you got a bunch of them. I just grabbed a picture off the internet. So you can see here's a bunch of what the banknotes look like from New Zealand. And I bet you all hope that you were having that 200 Turkish lira on the right-hand side of your pocket. We've been working on the security of banknotes. And there's all sorts of stuff, holography and optics. And what we're really after, and I talk to Professor Eckley about this all the time, it's looking, that piece of paper, that piece of polymer, it's about 100 microns thick, 100 micrometers thick. And we can print circuits inside that. I got to tell you, that's clever. We have individuals that are working on small modular nuclear reactors. So we're not talking like, big tower. No. These are about the size, maybe a little larger than a standard refrigerator. Not a little refrigerator for an apartment, but like, a person-sized refrigerator. And that's a small modular reactor. And this particular design can produce 300 megawatts. So the idea is, wait a second, we don't have the worries, or not so much, the worries that you find with other things about, nuclear proliferation and what's going to happen with the spent fuel. And we're going to have stuff with half-lives of 1 million billion years or something. No. It's a way different design, And it's relatively inexpensive. In general, you can get about 1 megawatt per $1 million. That's $1 million, but it's a megawatt. So this thing we're looking at would cost a lot. Well, you can scale it much smaller, much smaller. And the idea is that a small neighborhood can have their own small modular reactor. And we don't have to have these massive cooling towers and all the other issues associated with that. This is a big activity at the lab, small modular reactors. We also put one on satellite that is on its way over to Jupiter. It's kind of neat. What's this slide? Now, remember, we're just covering a lot of stuff, activities at the lab. And your dear friend, Professor Eckley, is involved with a lot of this. We'll get to some there in just a moment. It shows the disciplines that happen in electrical engineering. Now, I got to go back to this for a moment. I don't have to, but I'm just going to. That's that. Look, I have an undergraduate degree in physics. So it means I know a little bit about physics. And what I really know is that I don't know much about physics. And then the degree in math. Why? Because, you got to use some math tricks here and there to actually analyze stuff. And so the whole data analysis world and signal processing, et cetera, I'm not going to cover it here, but it all falls within the discipline of electrical engineering. You're drawing on applications from other types of disciplines. Some of the stuff, EE is not going to build a small modular reactor. We need some mechanical engineers, somebody who understands SolidWorks or AutoCAD and help in those things. It is a collaborative world. So again, here at the lab, we have 5,500 colleagues. I keep talking about that. We have over 2,700 doctorates, PhDs in all sorts of disciplines. Oh my goodness, we have all sorts of stuff. Well, you know what we're looking at in one of our other activities right now, and Ali was busy with this yesterday, or maybe the day before, wildfires. We have all sorts of wildfires in the United States, and you know, so do you. And so I love this, I love and I hate this satellite view of the smoke plumes coming from specific wildfires that were in your fine country about a year ago. Here's where it's close up there. This is where it's showing two things in this chart. On the left-hand side, notice what it's showing as on the axis, burned area in thousands of hectares. On the right-hand side, it's trying to present the number of wildfires in thousands that have been taking place over the last few years. Notice the data clicks out here at about 2017, 2018. But the bottom line is wildfires are everywhere. This is a shared issue for all of us. And we're working on that. We're trying to do some stuff. A few slides ago, I was showing you something about some drones flying in a swarm. They're small in Montana. This is another view from a drone in that area in Montana. And again, if you're an outdoors person, I got to tell you, this place is beautiful, just beautiful. That river that's going through it is wonderful. I chose this picture specifically because there's a small town called Libby, Montana. You can Wikipedia, you can see there's on the left side of the river, there's this little town. It's very, very nice. On the right-hand side of the river, you can just make an outline right along the river. It's like, hey, it looks like there's a sandy beach. This is great. I can be in a boat, a canoe, a kayak, and just going along the river, and it's beautiful. And then if I step on the ground on the right-hand side of this river, you run into the most polluted place in the United States. We're in Libby, Montana, up in the orange, up at about 11 o'clock in this dial. It's asbestos, and asbestos is everywhere, and it's terrible. It's a terrible situation. How bad? You're supposed to be in a hazmat suit on scuba if you're on the right-hand side of this river. Well, we're trying to build some sensors to help with that. So it's a big problem. And notice the multidisciplinary activities that are necessary. We have experts in chemistry, in detection of 10 micron size little fibers, asbestos fibers or vermiculite, in the presence of other stuff, as we're going to try to fly them on drones. And we're going to do this in October in Montana. And Professor Echte and I and our team, we'll be there. We're going to be at that particular place. We have devices that are going to go onto stands that we just plant in the ground. They talk via a mesh network, cellular and satellite, SATCOM, to get back the information to where we're going to be, all sorts of stuff. The fibers look like this. What are we using for our detection system initially? Raspberry Pis. There you go. Use some smart diffractive optical background techniques, optical signal processing. We know the mathematics is necessary. We know what we need to do to get this. It's a low signal to noise ratio, but we can do this. So I found it so nice to see in the agenda for your meeting that's going on today and tomorrow. You got a lot of individuals that are using, that is a smart little computer, a little Raspberry Pi and other things. It's quite good, quite good. We have a lot of them. Oh, there's math. Oh, you have to have math. Yeah, we get that. What we're trying to measure is this stuff. So again, this is really dragged out of a specific asbestos presentation. Bottom line is we're using a Raspberry Pi and photomicrographic techniques and some mathematics to see the fiber, which is right the lower right-hand side, or about 3 o'clock in this picture. You can see a little fiber. That's what we're trying to measure. We're going to fly it on these drones. This is one of our little conference areas that we work in all the time. Oh my goodness. Here we are. Got a bunch of people working on this activity. If you're curious, these are all free. The National Academy of Sciences in the US came up with this document about a month ago. And it's it. It's free. Here's where you can go get it in case you're curious. As it says, understanding and forecasting air quality. And specifically, it's on wildland fires, but it has other stuff too. It's really great. We're out in the field. We did these measurements. You've seen the picture on the upper right-hand side before. Those are the drones we were using. We popped some thermal imagers of various sensitivities and spatial resolution. And we can look at electrical grid. There you can see we're looking at a power pole with the intersection of some distribution lines by using a thermal imager. Understand again, what are we talking? We're talking about sensors and optics and thermal and power systems and all sorts of stuff. Multidisciplinary. Back in Montana, we had drones on top of other drones doing measurements, and that's all this is trying to show. Here's what it looked like in the infrared. So that's 138,000 volt kVA, 138 kVA transmission line, and it shows up really well with the cold background, the sky, and we can see the temperature variations with those lines. So no big surprise, you pump more current down a wire, it gets hot, right? We got this, that's how it works. And we can do that also on transmission lines and figure out if there are hot spots on the line itself. Here's a picture of some of the drones and sensors we've been using. And one activity that, again, Professor Eckley's been doing just awesome work on this. And I think it's representative of what we're experiencing with everyone that comes from your particular world and your academic institutions. Excellent work, and I thank you for that. One of my very dear friends, turns out, I think he grew up in the same neighborhood. It's a circumstance, right? Or just coincidental is where Ali was. And wonderful stuff. What he's involved with is wireless charging for vehicles. Say what? What, Peter? What? Yes. So what he's working on is we have a couple cars. We have one from Hyundai, and then the other one is this proto car from Porsche, which is like, oh my goodness, this is a great car. And we're looking to put antenna systems in the roadway itself at intersections, anywhere you have to stop. And then as the car is stopped over it or rolling over it while driving, it's charged. It's charged from the infrastructure of the grid that is buried or embedded into the pavement. That's great. His name is Barack Ospanichi, and he's awesome. Again, we saw this before. Let's get past it. We were doing some spatial, trying to figure out spatial resolution of various types of thermal imaging sensors. It's just some pictures. That's what we do. Here we are again. Why? Why do I hit this, youngsters? There's a PhD in a slide. We were looking at microbolometers. Let's go past that. We did a bunch of comparisons of different types of commercial devices, other things we could build, and see how good they are and which one we should be using to fly at 60,000 feet. So what is that in meter land? Something like 20,000 feet. Let's go 20 kilometers up in the air and look down at wildfires and see if we can resolve stuff. This is R&D straight up. We have a colleague of ours who has a very nice farm and horses and chickens and ducks and all that sort of stuff. We've been putting sensors and wireless systems out here. And here's another view from one of our drones. We're doing measurement stuff. We took this particular drone to 1,200 feet. What's that? Roughly 300 meters, 400 meters, excuse me. Let's do the math right, man. And it's got a specific type of sensor, boson-based radiometric from the company Fuhr, based in the Netherlands. And we looked down at this test area. It doesn't look like much. So what we did was put some wood inside this particular canister and light it up. And then these little dots that you can see here are small. They're about maybe 10 centimeters, 5 centimeters in diameter, about 5 centimeters in diameter. And we can light those also. So from a visible wavelength perspective, that's what we see. From a thermal perspective, this is what we see. Notice right at 12 o'clock, that's a drone that's also flying above this particular test source. What we were after was looking at the spatial resolution at various heights. Here we are right on top of it. You can see it's glowing at about 206 degrees. That's the price there. Let's see if this one plays. Maybe it will, maybe it won't. That's okay. Let's try it. Okay. Well, is it moving? Is it playing? I can't quite tell. There it goes, just a little bit. So we took that particular drone. Hopefully you can see those sources are arranged in something called an Archimedean spiral. And there's mathematical reasons to do that. But yeah, bottom line, what we're trying to do is go to different elevations and what's the spatial resolution of types of sensors on a drone, so we can have the drone way over the fire and still be able to resolve various things. So you can see we're just increasing in altitude. I'll get right past it. Again, this is from, as you can see, 600 feet, let's say it's 200 meters. Looking down, there are the vehicles. I think Professor Eckley, I think one of those vehicles is his. I think so. I don't know. Anyway, we're looking down, and here's what it looks like in the infrared. So again, easy to resolve stuff because, well, here's mathematics, image processing, trying to look at what the spatial resolution of the sensor was. Why do I hit there? Right there, you just cross physics, math, and optics. That's what we're doing with a specific type of thing. A different way of looking at it. So we had some data analysts come in and say, oh, instead of looking at it like this, let's modify it and manipulate the data and look at it in this way. And it is easier way just to stand up from the background of where the sources are. Again, we're back on this. In early April, there was a wildfire about, maybe 40 kilometers away from the lab where we work. And we went over there with some drones and we were measuring stuff. What? Remember that video from way back when? We had a white DJI Phantom 2 with a red canister box underneath it. We put sensors inside that red box. Well, some of the stuff was, okay, if we have a wildfire, what's happening to the temperature of the electrical transformers that are on a pole that's in the ground and the pole is on fire? So that's one of the things we're after. And here's just some pictures we had of this particular fire. It was not as devastating as some, not as devastating as those images we had of the 3 fires simultaneously underway in Turkey from back in 2017. But you get the picture. Other things we're trying to do, again, just this came up as, wait a second, if you look closely, maybe the resolution's good enough for you. If you look closely, on the left-hand side, there are wires. And of course, that's electrical distribution, 7,200 volts, and distribution. But if you look inside those little yellow ellipses, there's a darkened area, and that's a splice, where the wire itself, the distribution wire, was spliced together. Okay, great. It's kind of hard to see it in the visible, but on the right-hand side, it shows up relatively well with the thermal camera. So we're going to do an experiment. And the experiment is pretty straightforward. Can we fly a drone with one of those thermal imagers at some elevation and be able to see where the splices are in the distribution network? Why? Because those are points of failure. Most utilities don't know where they are. So if we can fly a drone around, we can categorize it. Catalog it, excuse me. Here's where the splices are. So if something's going to happen, this is where it's prone to fail. Here we are again. Yesterday, Professor Eckley was at a specific place working with the utility here again in East Tennessee. You can see some of the mountains in the background. The picture shows it all. We had a drone taking a picture of a drone that's looking at some people that were climbing the radio tower on the right-hand side to install some wireless transceivers, because we're trying to blanket that small city, population 10,000, with broadband rural wireless internet. So there's lots of stuff that comes into play, and you know what? It actually works. This is where we're going next. We're almost out of here, guys. This is where we're going next. We were asked by both NASA and, as you can see at the bottom, the U.S. Fire Service, and we're with the Department of Energy, and of course we're at Oak Ridge National Lab. That's where all those letters come from. If we can install some of our sensors in this particular big drone, and we're looking to do this, we're looking to put our sensors in the nose cone of this drone. You can see it right there. That thing itself, as it says, it's solar powered, okay? And it's supposed to have an 8-day duration at 60,000 feet. So check this out. We were going to do it in August. Looks like there's a delay. Looks like it's in September. We're going to have our sensors to measure stuff on the ground because there are still some fires taking place. We're going to launch this at the spaceport. Spaceport is sort of where it's not where Starlink satellites are taken off or launch rockets are taken off from. I think it's the other thing. I think the other guy, Bezos, has something going on. Anyway, So we're going to launch from the spaceport in White Sands, and then it flies, oh golly, 2,000 kilometers. It flies a long, long way over to San Francisco in the Bay Area where it will land. So the main thing is we want to image from 60,000 feet, 20 kilometers up in the sky, looking down at wildfires on a drone that is powered by the sun and lasts for 8 days. Oh, and by the way, the temperature is 60 below zero. So we have all sorts of challenges associated with that. This is a big problem. This is a big project. Hence, the big national lab saying, yeah, this is tough. Let's get to it. We have a test facility. And I think, again, Professor Eckley was over here at the TUAC, Technical Testing and Analysis Center, I think is what it stands for. And we're going to subject our sensor to all of these parameters where we can vary in a test environment just to make sure it's going to last at 60,000 feet for 8 days at 60 below zero. It's kind of fun. Got a lot of stuff. Notice this slide. I got it from the guy I've been making reference to, your colleague and mine. He's working on autonomous driving and autonomous communications to be able to talk to the device itself, the vehicle. So it's vehicle to something, hence V2X. And there are all sorts of activities that are involved. I think we're going to, about a month from now, I think we're going to get a car from Toyota that's supposed to be outfitted with all these different types of communication things, and away we go. This sort of shows it. There's a nice paper. You sort of follow, oh, get back here. A vehicle to the road itself, vehicle to cellular, vehicle to satellite, all things. And it's for autonomous driving. What's really of interest is what the title of this paper is, that latency, a cellular-based V2X. So can we rely on a cellular network? Does it have reasonable, almost statistical, absolute latency? That's problematic. That's a problematic thing. Trying to do it. This diagram is kind of nice, or I'm sorry, the chart's kind of cool because it says when you're driving at 100 kilometers per hour, here are the latency requirements for the vehicle to do this and that and this and that. So great, that's hooked up. That car is actually hooked up in one of our labs here. Notice in the picture on the lower right-hand side, the wheels are off, but we have dynamometers and other devices that are attached to the axles of the drivetrain to figure out how it's doing. So it's gotta work really quickly. Look at that pre-crash sensing warning. You have 20 milliseconds. So if you're doing something like using the cellular network to get that information from car one to car two, like I'm slowing down right now. There's a crash in front of me. You have, count them, 20 milliseconds to get that signal from one vehicle to the next through the infrastructure and then do something. This is a tough thing. That's what we're trying to do. So again, the bottom line is at the lab, we have all sorts of activities. I've just touched on a few. And what we try to do is have tests typically that we're going to do stuff in the laboratory. And from a utility perspective, then choose something and prove it in the lab, then prove it inside an electrical utility, and then scale it to within a region. And the picture we're here within a microgrid, we're using the island of Puerto Rico and its electrical system as an entire microgrid. And then we just do stuff there and then take it to a national scale. So last thing, see if this one works. Where'd the pointer go? I think it's silent. We're using commercial off-the-shelf drone up in the air. And we were trying to see what the thermal signature looks like through the tree canopy. So visible, it's hard to say stuff. In the infrared, we're looking right through the leaves. And you can see all sorts of stuff. That's a for real fire. And it's generated by an arc. So it's cracked insulator where there's arcing, and it started that fire right there. And Professor Eckley is right involved with this particular activity. He's done some really clever work with data analysis, playing mathematical tricks to analyze the data. Away we go. Thanks for hanging in there. My name is Peter Fuhr, and it's been my pleasure to bore you for a while with some of the stuff that's underway at Oak Ridge National Lab. And with that, I'm done.
Thank you very much, Professor Fuhr. So do we have any questions from the YouTube? Good.
Let me double check, because sometimes there might be lag. No, I think, there is none, because people hold their breath. I think, they're waiting to digest. So it might just, pop up. There is none as far as I can see, but just,
Let me start with
Yes.
with the question. Actually, like your topics are quite similar of what I was doing in my previous years, and actually my undergrad students did a sensor network graduation project, and now they are trying to put it in a rock breaking machine. Like they are converting the rocks to pebbles.
Sure.
The problem is like the environment is terrible. Like it's an extreme environment. We are losing Wi-Fi, we are losing the sensors and so on. So with your previous experience, like how would you design sensors in really harsh environments?
Oh, it's got to go remote. I mean, that's the thing. So as you said, we've had all sorts of work we've done with petrochemical companies around the planet. And although it's not as physically harsh as mining, oh my goodness, but we've done that too. The main thing is that there's always some sort of ambient condition that's tough to work in. That environment is tough. And in mesh networking world, if you're communication like yourself, mesh networking world, oh my goodness, it's try to design the network so no single point of failure. But if you just get something that's hard and it's smashed and that particular node goes out, oh, there's nothing to do. There's nothing to do. So try to use the communication infrastructure. Maybe cellular would be better. I think it's that old NASA thing. There's no single point failure. So even in your communication network, if a node goes out, make sure that there's a fault tolerant network design. Other than that, put it in a really hard titanium shell and hope that nothing happens. That's a tough problem.
I see. So, from your talk, I see that multispectral analysis would be actually a really good solution for most of the problems that you are looking for. So if someone wants to actually study signal processing, what do you suggest for him or her to do?
Oh, that's a great question. And let me hit the first part. Absolutely, we believe in hyperspectral imaging and multispectral scanners and all sorts of stuff like that. And that started when the lab, this predates me at the lab, but I was involved with this at NASA. We put multispectral scanners on a couple satellites that are on orbit, and they were ground imaging satellites. So the main thing, it's so simple initially. It was this multispectral scanner looking at the canopy of the leaves in Brazil to see if the rainforest is really being impacted. And you can just look for color changes, and it's going to tell those biologists something's up. I'm a firm believer that optical signal processing is a way to go. So I would actually, for such an individual, I'd say you need to go to a book on optics by an author named Klein and look at how in chapters 5, 6, and 7, how interference spectroscopy is actually done from an optical signal processing perspective. It lays out all the mathematics and says, here you go. And so what are you going to study? It's coherence-based stuff, autocorrelations, just understand how to do a transform. That's the start, and work with that. Other than that, the same discipline, but the mathematics can go from one to the other. There's a great book too. That's just me. Understand, I'm not a data analyst. It's not my purview. But it always falls, you always do stuff like yourself. If nothing else, in advising a dissertation student, like this is what you should do. See how it works.
Thank you very much. Professor Yarkan, do we have any questions, or do you have any questions?
Actually, I do many, but I'm checking the YouTube channel, as I said, just, if I can see anything. I think, Professor Murat asked one. Would you like me to transfer it to you, or shall I read it, or you just, want to go ahead, Professor
Go ahead.
Okay. Professor Murat asks that, is government mostly funding your research? How much support or demand on your research is coming from the industry? That was Professor Murat's question.
Okay, that's a great question. The lab itself, as you've heard me reference, it's big. And so with all the people, our operating budget for the lab itself is about $2.5 billion on the unclassified side. So that's that. We don't compete with the private sector, but we do a lot of work with the private sector. And in that particular case, we're not talking billions, but we're talking reasonable money. Let me dial this back and make it a little bit more personal. See if I get this right. RZA? Okay, did I say it right this time? I'm trying, Murat, I'm really trying.
Yeah, please go back to Ali, because I'm forcing you to say RZA. It's only me. That's me.
I love it. So in the group that Ali and I are involved with, we have ostensibly 17 people inside our group. And there are various disciplines. We have data analysts, we got web programmers, we got firmware people, we got Raspberry Pi sensor people. We have quite the team. And our annual budget just for our team is around $18.5 million. So we are a well-funded little machine. And inside that, probably $2 million comes from industry. So that is right inside our group. And we work for Honeywell and Siemens and a lot of big industrial firms on just helping them with the thing that's of interest. Here's an example. There was a specific offshore oil drilling issue that took place in the Gulf of Mexico. And what happened was there was a specific thing that sits on the floor of the ocean. And it's the interface between the rock underneath, and then here is something called a blowout preventer, and then the drill string. So what am I talking about? We're a large company, and we drill holes in the earth. And specifically offshore, there's a lot of oil. So we're going to drill down, we're going to submerge our drill bit down to the interface with the earth, and then we're going to start drilling. So we're going to go in water that's 10,000 feet deep, 3,000 meters, and then we're going to drill a hole that's 20,000 feet underneath the earth, underneath the ocean. Okay. What's going to start coming up are little pieces of rock and debris and junk and some hydrocarbons. And here comes the oil. So we just went into the offshore drilling business. This is conjecture, Murat. So we're just doing this. What happened in the Gulf of Mexico is the clamp that is meant to shut down the well if something happens failed. And that blowout preventer, it just exploded underwater. And all of a sudden, there was a hole in the ground, in the ocean, bottom of the ocean goes way down deep. And here comes a geyser of hydrocarbons and polluted the Gulf of Mexico. Bad news. It was something called the Deepwater Horizon. They actually made a movie about this because it blew up and it was awful. Well, what came out of that was the following. It took months for actually to close that. We got asked by the drilling company, Transocean, whose drill it was, and Halliburton, the company that was actually running the drill, and British Petroleum, right out of the UK, if we at the lab could design a new blowout preventer, one that doesn't rely on 1950s technology like the thing that just exploded, and can we do this? So I was lucky enough to be, I'm good friends with a director of technology for Transocean. They have 30 or 40 ships right now. They're going around the world drilling holes. So I said, yeah, sure. And I gathered together a team of about 20 people, subject matter experts from the lab in all sorts of disciplines. And through 2 weeks, we designed a new blowout preventer. And what it relied on, this is wonderful for you physics and EE people, is electromagnetic field theory. So instead of having the current configuration, is you have a giant cylinder of pressurized air. And if you need to, you just open the valve. We're at the bottom of the ocean. You open the valve and these two pistons come and they just shear off the pipe. They just close it. Okay, fine. And it fails. So what we did is we said, no. Let's have a battery at the bottom of the ocean and use inductive powering. So basically what's going to happen is we have a couple coils that go around the drill string itself. It's a pipe made of steel. And we just put a bunch of energy into it. And it will induce a current flowing in the steel. This is straight up Faraday's law. So we got a current that's here going, and it gets so hot, it melts it. It melts the pipe. And we proved it. And it works. So Shell and Transocean decided, oh, we like this so much, let's go form our own company and make these $50 million devices. They did that. We do similar work for all sorts of utilities or all sorts of private concerns. Cut that back to the chase. That was a lengthy, maybe off the track little anecdote. Our operating budget, like I said, is basically $17-18 million. And around 10% of that comes from industry. And the rest of it comes from various other sources. So I'm sorry about the lengthy thing. Just to give you an example, it was a big problem. It's like, I think we can solve that. And we did. My slides I'll make available. There's a lot, the videos are inside there. It's a hefty file. Use and abuse it as you wish. I appreciate the time. I appreciate the patience of you listening to me just ramble on and on. But I was trying to present multidisciplinary research that's really underway. If you're doing a singular stuff, good for you. If you're a delta function in that knowledge space, good for you. Chances are you're going to have to ask somebody else some questions too. It's good to work in a team.
Thank you very much. You are absolutely right. So we would like to thank Professor Fuhr for this talk, and I would like to go forward with our session. So
I think there is one more question, Professor.
One more question. Okay.
On YouTube, just popped up. With your permission, let me read it out.
Please.
It says that Mehmet Kara, thanks for the presentation. What kind of infrastructure should it have in order to use the drone technology you mentioned? Can we use it to prevent forest fires in our country? So basically the general infrastructures, I think, is the main question here.
Oh, I appreciate that. Typically, at least here in the US, I'm not sure exactly in those locations on that chart that I showed, where the smoke plumes are coming out the south and southeast part of your country, which is beautiful. And I've been there and it's very nice. And thank you for that. Anyway, it's rolling topography in general. So it's the communications for the drones to try to figure out what they can measure. And you got to just make a decision. I'm either going to go satellite communication, I'm going to go SATCOM, or I'm going to use cellular. And the rest of the things are kind of tough. You could set up like little other communication networks to talk to the drones, but in trying to get beyond visual line of sight. So you get away, versus 100 meters, I need to get a few kilometers away, and now my drones fly there. You need a cellular infrastructure, and you can build it yourself. You can do it yourself, DIY 5G system, and put that on a drone or a balloon, and put that cellular network up in the sky high, and then have your drones talk to that, and then down to the ground. I was fortunate enough about a month ago to be at a fairly hefty unmanned aerial systems for utility applications conference. It took place in the city of Atlanta here, and there were probably 100 drone vendors and 3 or 4 communication vendors. And to get beyond visual line of sight, specifically for these fires, you got to go cellular. And that is the collective decision. That's all. I could reference all sorts of stuff. Just let me know.
Okay, thanks. And let me just, one more time check. I don't see any question on YouTube, but with your permission, I have one question, Professor Fuhr.
Well, hold it. Now, hold it. If it's an easy question, yes. If it's a difficult question, aim that at Ali.
Okay. Then you guys decide. But just my question actually, would be related to this. Actually, we already established the basis. But let me just, ask one more time with your permission. So basically, the research that you talk about in Oak Ridge National Lab is, as you stated, obviously multidisciplinary. That's obvious. But since this conference at the end of the day is an undergraduate academic conference, I would like you to just emphasize, maybe prioritize the topic, because your background starts from physics, which I would love to hear it from you. So if you were to prioritize the topics and the equation that you showed us just in one single line, I would love to have it in here with your permission, Professor.
Yeah, of course. So I get asked at different times because I am also a faculty member at the University of Tennessee. Tennessee has about 35,000 students associated with it, and there may be 1,400 in electrical engineering and computer engineering. And so I get asked frequently, like, what should I study? What should I study? Both going right into college, you know, what should I study? Or graduate school, what should I study? If you have that bent about, I just want to understand everything I can about something, that's a doctorate. We all know this, that you're going to, you know, deep dive into a technology area. So you just have to find the one that you really find passionate. You know, is it optics? Maybe. Is it, you know, wireless communications? Maybe, or something like that. If you're looking like, I want to get a degree that's going to get me a quick job and something that I'm going to enjoy, without a doubt, I do not hesitate in saying, understand how to program a Raspberry Pi and understand firmware and that level of programming, because the needs are everywhere, just everywhere. So that's really it. I'm a doubling. I'm saying go over in computer engineering, not computer science, because you know, don't understand that. My perspective. Go in computer engineering, so you understand a bit of hardware and you certainly understand the software. And just look at the ads, the job postings that are out there. That's for that. If you want to go dabble in quantum computing and quantum engineering, and we have a dear colleague of ours who's doing that, that's esoteric. Good for you. Go get a degree. Go become a professor somewhere. If you want a practical experience, number one, computer engineering, and understand it with, or double E's, right? Those things are so close. And that's it. If you can't tell by my voice, I'm very emphatic about that. So I think that's it. Your mileage may differ, gentlemen. I don't know.
Okay, thanks, Professor. And just, you know, final check, because that was an insightful and knowledgeable presentation. But, you know, I see no further question on YouTube. And Professor Baykash, the stage is yours.
Thank you again.
Thank you very much, Professor. So let's start our normal session with the presentations from the students. We have a great chair, Adiriza Ekthi. So I'm proud to say that he's one of the heroes of this conference. He accepted to become the chair. He suggested Professor Fuhr to us. So he's a senior member of the IEEE. He did his bachelor's degree in Mercer University. Afterwards, he studied in University of Florida, Tampa, and then he got his PhD from the Texas A&M University, all in electrical engineering. And afterwards, he was an assistant professor in Balıkesir University, and he was the division manager of the Hisar Laboratory of TUAC Bilgem. He works on statistical signal processing, wireless propagation, channel modeling, and at the moment, he is also in the Oakville National Lab. And also, yes.
We have to stop here the live stream.
Okay.
Because this will be another video on YouTube.
Okay. So let's stop it.
So shall I stop it and then?
Okay. See you in a minute. Okay.
Okay.
Thank you, Dr. Fuhr.